pipe sizing and how to calculate inlet pressure for a loop piping system. Now, a natural gas pipeline is 60 kilometers long. The gas flow rate is 5.0 million cubic meter per day at 20 degrees Celsius. Calculate the minimum diameter required for an inlet and delivery pressure of 8.5 megapascal absolute and 5 megapascal absolute respectively. Use the general flow equation with the modified Clebris-White equation, wide friction factor. The pipe roughness is 0.020 millimeter. In order to increase the flow rate through the pipeline, the entire line is looped with an identical diameter pipeline. Assume the same delivery pressure. Calculate the inlet pressure at the new flow rate of 8 million cubic meter per day. The gas gravity is 0.6 and the viscosity is 0.00119 pounds. The compressibility factor Z is equal to 0.9. Base temperature is 15 degrees Celsius and base pressure is 101 kilopascal. Now, let's begin. Now, we want to do pipe, what we call pipe sizing. Now, what we're going to do now is we're going to assume value for D. Let me say D is 400 millimeter. Now, if it is 400 millimeter, assuming it's 400 millimeter, so we are going to now use it to calculate our Reynolds number, calculate our transmission factor before we now apply the general flow equation. Now, this is a formula for the Reynolds number. We need to calculate it with 0.5134 times base pressure divided by base temperature times bracket open gas gravity times the flow rate divided by the viscosity divided by the density, the diameter. Now, what we're going to do now, let's just write down the given information. Now, the given information is we're given the length, which is 60 kilometer. We are given the flow rate, which is 5 times 10 raised to power 6 cubic meter per day. Now, we are given the gas temperature, which is 20 degrees C, converted to Kelvin is 20 plus 273. This will give us 293 Kelvin. Now, we are also given P1 to be equal to 8.5 megapascal. We have P2 to be equal to what? 5 megapascal. Now, E is equal to 0.020 millimeter, and then gas gravity is 0.60. The viscosity is 0.000119 poise, and the base temperature is 288 Kelvin. The base pressure is 101 kilopascal, and the compressibility factor is 0.9. Now let's calculate the Reynolds number here. Now we have 0.5134 times bracket open 101 divided by 288 bracket close bracket open times bracket open 0.6 times 5 times 10 raised to the power 6 divided by viscosity, which is 0.000119 divided by 400. So let's calculate. Now we have 0.5134 times 101 divided by 288 times 0.6 times 5 times 10 raised to the power 6 divided by 0.000119 divided by 400 equal to, so we have 11347,470. It's our Reynolds number. Now we're asked to use modified Colobric's equation. So the modified Colobric's equation, where F is equal to -4 log bracket open E all over 3.7D plus 1.4125F divided by Reynolds number. Now to base 10, bracket close to base 10. Now that means now we have known our Reynolds number. Now we are going to do a iteration. We're going to do iteration. So we are going to do an iteration here, assuming F is equal to 20. Now we use that, say F is equal to -4 log bracket open E. E is 0.02. E is 0.02 divided by 3.7 times D, which is 400, plus 1.4125 times 20, we assume 20, divided by Reynolds number. Divided by Reynolds number, which we have as 11347,470 base 10 bracket close base 10. Let's work this out and see what it will give us. Now we'll now make use of our calculator. we say minus 4 log 0.02 divided by 3.7 divided by 400 plus 1.4125 times 20 divided by 11347 470 bracket close, so equal to, so we have 19.18. So since it's 19.18 and it's not the same with this, now we are going to use this, we're going to do an iteration again. We're going to use 19.18. So assuming this is 19.18, assuming f now is now 19.18. So we now find the f on the left hand side. So we have minus 4 log base 10 of 0.02 divided by 3.7 times 400 plus 1.4125 times 19.18 divided by 11347 470 will now be equal to, let's calculate this again to see what will be, we'll have minus 4 log bracket open 0.02 divided by 3.7 divided by 400 plus 14125 point 1.425 times 19.18 divided by 11347 470 bracket close. So now we have 19.19. Now let's still use this our 19. Let's use our 19.919 again to make an iteration. I will just say let's stop here because the difference is not much. Okay, let me still use that 19 again. Now assuming f is equal to 19.19 now. Now we'll now calculate f now on the left hand side. So minus 4 bracket open 0.02 divided by 3.7 divided by 400 plus 1.4125 times 19.19 divided by 11347 470 base 10 is equal to what now? Let's see what to give us. Now we'll just say minus 4 log 0.02 divided by 3.7 divided by 400 plus 1.4 to 4.41 0.4125 times 19.19 divided by 113,47417 bracket close equal to, so the final answer is 19.19. So that is it. So this will be it. So you see, this value is now equal to this. So now we're going to use f to be, that is f is the transmission factor. So but again, let me go back. Again, this, when using these formulas, I did not actually give you the meaning of all this. So now for a Reynolds number, you have this to mean Reynolds number. This is dimensionless. Then you have a base pressure. You have a base temperature. So the base pressure is in kilopascal. The base temperature is in Kelvin. Now the G is gas gravity. This is dimensionless. So now, and Q is the flow rate of the gas, which is in meter cube per day. Then you have U is mu, which is the viscosity, which the unit is in poise. Then you have V, which is internal diameter. This is in what? Millimeter. Now, this is also in millimeter. This is dimensionless in millimeter. So that is it. So now, where, I'll just say where this whole for this formula. Now let's now go here. We now, since we have gotten this, this is transmission factor. Now, since we have gotten the transmission factor, we now have to make use of the general flow equation. So this is the modified transmission factor. So let's use the general flow equation. So the general flow equation is when you say the flow rate is now is equal to 5.747 times 10 raised to 4 minus 4 F, which is the transmission factor, times bracket open the base temperature divided by the base pressure times bracket open P1 square minus P2 square divided by gas gravity times divided by gas gravity divided by gas temperature divided by the length of the pipe segment divided by the compressibility factor, all bracket close, all raised to power 5 times d raised to power 2.5. Now, having seen this, I will now say where Q is the flow rate, is the gas flow rate in meter cube per day. Now F is the transmission factor. This is dimensionless. So we now have the T subscript B is the base temperature. The base temperature, this is in Kelvin. Now we have the base pressure. The base, this is in kilopascal. We also have what we call P1. This is the upstream pressure, or you say the inlet pressure. This is in kilopascal. Now you have P2, which is the downstream pressure, or you say the outlet pressure. It's also in kilopascal. And now the next one is G. G is gas gravity. T subscript F is gas temperature. This is in Kelvin. Now the Z is the what? The compressibility factor. This is dimensionless. This one is also dimensionless. This is dimensionless. Now D is what we call the internal diameter of the pipe segment. Now, which is in millimeter. Then L is the length of the pipe. This is in kilometer. Now, this is in kilometer. So we are going to now substitute the values. Now we have Q, which is what? 5 times 10 raised to the power 6 equal to 5.747 times 10 raised to the power minus 4 times 19.19 times 288 divided by 101 times bracket open. Now the pressure at the inlet P1 here, P1, which is this is 8.5 megapascal. Now we need to convert this to kilopascal because the units there is supposed to be in kilopascal. So Let me do it there. Okay. It's supposed to be in kilopascal. So to convert this, let me do it here. So now P1 is 8.5 megapascal. So to convert this to kilopascal, we have 8.5 megapascal times now 1000 kilopascal is equal to 1 megapascal. So this will cancel out this. You will now have 8500 kilopascal. Now the same is applicable to P2, which is 5 megapascal, which is 5 megapascal times 1000 kilopascal divided by 1 megapascal. This will cancel out. You have 5000 kilopascal. So that is what we're going to use in this equation. This is going to be 8500 square minus 5000 square divided by 0.6, because the gas gravity is 0.6, times 293, because the gas temperature is 293, times 60, because the length is 60 kilometer, okay, times you have compressibility factor 0.9, all raised to power 0.5 times d raised to power 2.5. Now we're looking for, we're calculating for d. We want to calculate to see if this value of d will be close to what we have assumed initially, what we assumed here. If it is not the same, we now have to recalculate again. So now let's now make use of our calculator to calculate this. So now let's make d the subject of formula. So we have d raised to power 2.5 is equal to, now we will now use this to divide this, and this, with the whole of this to divide this. So now, in order to move the whole of this to this other side, so now what we're going to do is we have 5 times 10 raised to power 6 divided by 5.747 times 10 raised to power minus 4 times now also divide by, now we're going to times this one will times this, so now times 101 divided by 288 times this one 19.19, because this one will divide this with multiply this, same thing. Now the whole of this will go to this side, so it will now be this one down here, which is 0.6 times 293 times 60 times 0.9, we multiply this, so we'll now say times 0.6 times 293 times 60 times 0.9 divided by 8500 square minus 5000 square, all raised to power 0.5. Yes, 0.5. So that is it. So this is it now. Now let's use our calculator to punch this out now. Let me see whether there is any mistake there. So no mistake. Now let me just calculate. So now we'll just say 5 times 10 raised to the power 6 times 101 divided by 5.474. No, not 474. 747 raised to power minus 4 divided by 288 divided by 19.19 times bracket open 0.6 times 293 times 60 times 0.9 divide by bracket open 85,000 square minus 5,000 square bracket close raised to power 0.5 equal to, so I have 2,254, sorry, 53, no, 2,258,658.06.603 254,706. So d raised to power 2.5. So if we divide the powers by 2.5, so we have d, because this will cancel out this, we have d equal to, now d will now be, so 2,253,658.603,254,706 raised to power 1 all over 22.5. Now let's, it will now give us 254,706 raised to power bracket open 1 divided by 2.5 bracket close equal to, so what we have here is 3 314 348 millimeter. So it's far from the assumed value. So now what we're going to do is we're going to use this value to solve, to calculate now our Reynolds number. We have 348, so we use it to calculate our Reynolds number. So now let's now recalculate the Reynolds number. The Reynolds number is equal to 0.5134 times bracket open base pressure divided by base temperature times bracket open gas graph times the flow rate divided by viscosity divided by the internal diameter. So now we have now 0.5134 times 101 divided by 288 times 0.6 the gas gravity times 5 times 10 raised to the power 6 divided by 0.000119 divided by 348. That is what we got now. Now let's put it here. So let's put it here. We have 0.5434 times 101 divided by 288 times 0.6 times 5 times 10 raised to the power 6 divided by 0.000119 divided by 348 equal to, so we have 13,043,069. So what is it? That means, so that is what we have now as our Reynolds number. Now let's assume F is 20. Now let's use it to look for F by intuition now. So now we'll now say log for log E, which is the roughness, pipe roughness, which is 0.02 divided by 3.7 divided by 348, which is what we get calculated now, plus 1.4125 times 20, we assume 20, divided by the Reynolds number 13,043,069. So now what we read the F now. Let's calculate. We have minus 4 log 0.06 divided by 3.7 divided by 348 plus 1.4125 times 20 divided by 13,043,069. Now we have 19. This is now 19.01. So we have 19.01. 19.01. So now assuming f is what? 19.01. So let's look for f now. We have f minus 4 log 0.02 divided by 3.7 divided by 348 plus 1.4125 times 19.01 divided by 13,043,069 base 10 equal to what? Now, so say 19.01. This will give us 19.02. So the final answer is 19.02. So now let's now make use of this 19.02 to solve for D here now. Now let's just copy this whole thing. Let's go here. Just say D now. This raised to power. Okay. Now let's say D raised to power 2.5 will now be equal to 5 times 10 raised to power 6 divided by 5.747 times 10 raised to power minus 4. Now times it was 101 divided by 288 divided by 19.02, because that is what we have now as our f. 19.0. So we have changed this. That is only what we're going to change there. So times bracket open 0.6 times 293 times 60 times 0.9 divided by 8,500 square minus 5,000 square, all bracket close, all raised to power 0.5. Now let's work it out now. Let's see what the D will now be. So whatever we have will be raised to power 1 all over 2.5. Now let's calculate this now. So we have 5 times 10 raised to power 6 times 101 divided by 5.747 raised to power minus 4 times 10 raised to power minus 4. Now divide by 288 divided by 19.02 times bracket open 0.6 times 293 times 60 times 0.9 divided by bracket open 85 square minus 5,000 square bracket close all raised to power 0.5. So this will give us what? This will give us 2 million. Let me see. What did we have the other one? 2 million. So we have 273,701.713,799,044. So now our internal diameter will now be what? Now let's find this now. So let's say raised to power brackets open 1 divided by 2.5 bracket close equal to 3, 4. So what we have here is 348.9. So 348.9. So roughly is 349. So we use 349 millimeter. If you reiterate, you will get 349. So it will not be far from it. So this is the final answer, the minimum diameter. So this is the minimum. This is the minimum internal diameter of the pipe. So now, since we have gotten this, we will now have to go look at we look at pipe data, look at the information there, look at the diameter that is closer to this value. Now from there we can now select the minimum pipe size of this system. But now let's now proceed as if, since we don't have that information here now, so let's proceed with this value 349 millimeter to solve for further information, for further this thing. So now when you go back to what was given, now here they said calculate the inlet pressure at the new flow rate of 8 million cubic meter per day. Now we are asked, now let's say in order to increase the flow rate through the pipe, look at it here, in order to increase the flow rate through the pipeline, the entire line is looped with an identical diameter pipeline. Assuming the same delivery pressure, calculate the inlet pressure at the new flow rate of this unit. Now let's go back. Now that means that from this we are asked to calculate the internal inlet pressure. So to get the inlet pressure, now this is the flow rate. You are from A to B. So here it is looped here now to this place. Now it means that what is coming here now is 8 times 10 raised to power 6 meter cube per day. That means at this point, since it is identical pipe, so what will be flowing through this loop will be the same, will be half of this. So will be 4 times 10 raised to power 6 metric cube per day. So here will also be 4 times 10 raised to power 6 metric cube per day. So here now you can see they have increased the flow rate from 5 to 8. So since we have known the flow rate from here to here, and you see the distance from here to here is the 60 kilometers. So everything is given now. We're going to now say the flow. We are going to use the general flow equation, which is Q is equal to 5.747 times 10 raised to power minus 4 F times bracket open the base temperature divided by the base pressure times bracket open P1 square minus P2 squared divided by gas gravity, gas temperature, the length of pipe, the compressibility, all in brackets close raised to power 0.5 times d raised to power 2.5. So now what we're going to do now is we're going to calculate for this the inlet pressure. So the inlet pressure now, what we're going to do is we're going to say Q now is 4 times 10 raised to power 6 equal to 5.747 times 10 raised to power minus 4 times 19.02, because now what we're using is 19.02 times 101 divided by 288. The temperature sorry, here is 288. Made a mistake. The base temperature is 288 divided by the base pressure times, let me see, bracket open. We're looking for P1 square minus, now since they say delivery pressure will still be the delivery pressure will still be 5,000 squared divided by gas gravity 0.6 divided by gas temperature 293 divided by the length of the pipe divided by 0.9, the compressibility factor, all raised to power 0.5 times 349 raised to power what, 2.5. Now let's solve for P1 square. So let's now make use of make P1 square, make it subject of formula. So now we're going to say P1 square minus 5,000 square all raised to power 0.5 will now be equal to 4 times 10 raised to power 6 times 101 divided by 5.747 times 10 raised to power minus 4 divided by 19.02 divided by 288 times 0.6 times 293 times 60 times 0.9 raised to power 0.5 divided by 349 raised to power 2.5. Now let's work this thing out now. Now to remove this 0.5, we square both sides. So now if we square both sides of this equation, this will cancel out this. So we have p1 square minus 5,000 square will now be equal to the whole of this square. So now let's work it out. We have 4 times 10 raised to power 6 times 101 divided by 5.747 times 10 raised to power minus 4 divided by 19.02 divided by 288 times bracket open 0.6 times 293 times 60 times 0.9 0.9 bracket close raised to power 0.5 divide by 349 raised to power 2.5 equal to this. So the whole of this will now be, the whole of this inside now will be 5.1454,602,278,24 square. So now we square this. Now our P1 square will now be equal to 5,000 square plus 5495.154602,278,24 square, which will be equal to plus 5,000 square equal to this. So the whole of this is the same thing as 55,196,724.102.9 3971. So that means P1, taking the square root of both sides. So P1 will now be the square root of, or I can say now raised to power 0.5 is the same thing as saying the square root. So what we have here is 7,429 kilopascal. So this is invariably 7.43 megapascal. 7.43 megapascal. So this is the inlet pressure that will give us that. So you see, on this ground, you see the pressure drop. It has reduced the pressure drop and also increase your flow, your flow rate. The pressure drop reduces and also it increases the flow rate. So this is the final answer. Thank you for watching till the end of this program. It is the end of this tutorial. Have a nice day. Do well to subscribe whenever I make new videos so that you also be the first to see it. Thank you and God bless.